Thank you for inviting me here. It's a great pleasure and a great honor. Thank you so much. Today I'll talk to you about human-robot interaction as well, similarly to Alessandra, but I'll take a different point of view. I'll talk about humans interacting with robots. So Alessandra was telling you about how to make robots more capable of social interactions with us. I'll tell you a story about us humans. How do we actually perceive robots? How do we treat them? Do we treat them as intentional social agents, or do we treat them as mindless machines? So after Alessandra's introduction to ICAB, I think I don't need to introduce ICAB anymore. My work is also very much done with ICAB and humans, as I said. So I'll start with an extract from a movie that you probably have, most of you probably have seen. And here it goes.
Could machines ever think as human beings do?
Most people say not.
You're not most people.
Well, the problem is you're asking a stupid question.
I am?
Of course, machines can't think as people do. A machine is different from a person. Hence, they think differently. The interesting question is, just because something thinks differently from you, does that mean it's not thinking?
All right, I'll leave you with that last question. If something thinks differently, does it mean it's not thinking? This is the leitmotif of our research, of the research of my group that I'll present here. And the question is, do us humans attribute thought processes, feelings, emotions to robots? In other words, more philosophical terms, do we adopt the intentional stance towards robots? So what is the intentional stance? As I said, it's a philosophical concept. And the idea here is that we as humans need to be able to explain and predict behaviors of our system, other systems in the environment. So we find strategies to be able to explain what is happening. With other humans, we adopt the intentional stance, meaning we attribute mental states to humans. So when I see someone grasping for a glass, I explain their behavior, that they wanted to drink, that they believed that water will ease their thirst. Wanting, believing, these are mental states. However, if a coffee machine stops pouring coffee, or a car stops because I pushed the brake pedal, I don't say that the car wanted to stop. I don't explain the behavior of the coffee machine that it wanted to be mean to me and stop pouring coffee. No, I explain the behavior that was designed to behave in such a way. Now, you can probably already see that robots might actually fall in between these two categories, especially humanoid robots, because they look like humans, they might behave like humans, but yet there are artifacts. So the question is, will we actually attribute thoughts and feeling processes to those machines? So that's the key question here, the intentional stance towards robots. And the first challenge that we have met in my lab was to actually operationalize this question. What does that mean? This is a philosophical question. How do you actually put a philosophical question into empirical research? How do you quantify if someone adopts intentional stance or not? So in order to do that, we developed this kind of test, the intentional stance test, where people see scenarios like those one that you see here on the screen, and they have two types of descriptions of the scenario, of what is happening in the scenario. And one description is with intentional terms. ICAP was trying to cheat, right? And the other description is very mechanical. ICAP was unbalanced. And people can choose by moving this slider which description they think fits best. And this way, we can sort of measure how much people attribute intentionality or thought processes to robots. Now, the interesting question that we have asked was, can we then identify at the neural level what sort of neural processes are underlying this kind of attribution of mental states towards robots? So we have learned that humans do adopt intentional stance to robots to some extent, and we have learned that from this test that I just showed you. And now what we wanted to do is redo this test while we measure people's brain activity, as you see here with EEG. And based on this activity, we wanted to see whether we would be able to predict what sort of attitude a person would have. In order to do that, we asked our participants to first, before giving them any task, to just come to our lab, we prepare the head, we put the EEG cap on, and we ask them just to relax. So it's called a resting state EEG. They are just thinking of anything they want to think while we're measuring their brain activity. And after that, we look at the data, and what we actually found is that we were able to predict from their brain activity whether they would attribute intentional stance, adopt intentional stance or attribute mental states to the robot, or adopt the design stance. And this is quite striking, because maybe someday in the future, we'll be able to predict from neural activity of our participants, users, what sort of attitude they will have towards a robot. Because at the end of the day, intentional stance is an attitude. I treat a robot as an intentional agent, social agent, or I treat it as a machine. And that has consequences for how I will interact with the robot later. These data showed us that individual preference towards the intentional stance can be actually decoded from neural activity at rest. All right, so far I told you about people's spontaneous stance towards robots, but the question of interest is, can we actually modulate the stance by various factors? For example, human-like shape, for sure, plays a role in whether we attribute mental states or not. Human-like behavior as well, and perhaps socio-emotional bonding, something that I think is the theme of today and probably most fits to the theme of this meeting. So I'll talk about the two latter points: the human-like behavior and social-emotional bonding. So we thought that perhaps when we create an atmosphere where robots and humans are doing tasks together in such a way that they feel the robot being their teammate, or they feeling that they're kind of social partners in an activity that they would do otherwise with other humans, maybe that would make people more likely to adopt intentional stance towards the robot. Why? Because if a robot plays with me or does a social activity with me, the robot is more like me, especially if it behaves more human-like. Therefore, I'll be more likely to attribute mental states to the robot because I attribute them to myself as well, right? So we created a task where participants did the test that I just told you before an interaction with the robot. Then they interacted with the robot. And then we did the test again after. And we wanted to see if actually this test would, so the score would increase, so they would adopt more intentional stance. In the task, we thought, what is a sort of a social emotional bonding situation in our lives that we would usually do? And we thought of going to the cinema together. We'd go to the cinema, we watch movies with our partners. So why don't we create a situation where the robot and the human watch a movie together, and the robot, importantly, in one condition, behaves in a human-like way because it will react to the events on the screen in a very human-like way, emotional way. And in another condition would be very mechanical. So let me show you the experimental manipulation. So what you see here is what they're seeing actually on the screen that they're watching together. And you see that the human cannot stop, they cannot help but laugh together with the robot. This is socio-emotional bonding. So in fact, after we presented this to our participants, their scores in intentional stance test increased, meaning they adopted more intentional stance in the human-like condition. But in the mechanical condition, where the robot was just beeping, it went like beep, 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 beep. In that condition, there was no difference before and after in terms of treating robots as intentional agents. Another task that we've done in a very similar way was team play, where the human and the robot had to do a task together. And the task was to move a cursor to a target, but they had two complementary roles. So one partner had to move the cursor, and the other one had to confirm that the cursor is already on the target. And this is how it looks. You see the cursor going, and now the human participant had to confirm. In this case, when they were playing together, we again saw an increase of adoption of the intentional stance, so increase of attribution of mental states to the robot. And so based on these data, we can say that social-emotional bonding and sharing tasks increase the likelihood of adopting the intentional stance. But now the question is, can we also take the intentional stance down and actually decrease the likelihood of adopting the intentional stance? So in this experiment, we asked our participants to play in a duet with the robot, play a musical sort of sequence. And in one condition, the robot was making errors, but human-like errors. In another one, very mechanical errors. Let me show you how it looked. So here you will see the human-like error. It will just swap two taps, which can happen to a human. Right now, it happened. It played the wrong tap. And you'll see in a moment the mechanical error, which will be very clearly mechanical. I'm sorry that you will probably hear repeating this. And you see the robot goes into a loop back and forth, and this is something that wouldn't happen to a human typically. So with this kind of manipulation, we actually observed what you see there in the data. We observed that people, after playing with a mechanically erring robot, they decreased the likelihood of attributing mental states to the robot. And interestingly, there was another very interesting behavior that we observed on the humans. They also increased, they decreased variability in the way they were performing the task in the human-like condition. And decrease of variability is a way of signaling between us the willingness to cooperate. We try to be more predictable when we want to cooperate. So that is very interesting to see that humans were kind of implicitly signaling to the human-like robot that they are willing to cooperate. All right, machine-like robot erring decreases adoption of the intentional stance and cooperation behavior. So the final part of my talk will be about nonverbal communication and other social mechanisms, not only the intentional stance. And Alessandra was talking about a lot of social signals that we display in social interactions. One of them is mutual gaze. That is extremely important, looking into eyes of one another. So what does it mean to look into the eyes of a robot? Does this actually activate in our brain social cognitive mechanisms? Do we treat this as a social signal? Because with other humans, it's an extremely potent signal. We know it all, right? But here the question is, these two cameras in a robot, are they treated like eyes? Are they treated like a social signal? So we designed an experiment in which this time participants played a competitive game with a robot. It's a very funny game because they had each of the partners, so the human had a kind of simulated car, the robot had a car as well, the cars were going in to one another, it was of course on a screen. And if the cars went too close to each other, they would crash and they would lose a lot of points. But if the human went straight ahead and the robot deviated, then the human won and vice versa. So one needed to sort of take a little bit of a risk in this game, but the important manipulation was that when they were making the decision about whether I want to go straight ahead or deviate, the robot either gazed at them or gazed away. And this is kind of a poker situation. I'm just about to make my next move, and my competitor is looking in my eyes. What do? Do I bluff? Basically, this is how the experiment looked. You see the cars, they stop, and this is the moment when the robot actually looks at participants or looks away. We measured a participant's EEG signal as well, and our data show that when the robot looked at them, this delayed participants' decision. So this really affected the way they were able to play in that game. And again, in a poker kind of situation that could be detrimental for them. So that means that our brain processes this kind of signal as a social signal. And we also see it at the neural level, that actually this kind of mutual gaze made a huge difference in our brain and the brain activity of our participants. Okay, the very final part of my talk is about social signals again, but I will focus on the application area. Because the question is like, why do we even bother with creating social robots? Why do we want to have intentional agents around us that are artificial? What difference does it make? And I'll tell you that, yes, it does make a difference. It does make a difference for clinical applications. So robots can be very helpful in being assistants for training and therapy for children diagnosed with autism. This is because there's a lot of research now showing that children with autism open up towards artificial agents. They're very much more likely to interact and engage in a therapy with a robot than with a human therapist. So if that's the case, then perhaps we can use this opportunity and actually use robots to help them training social skills. And this is the direction we're going in IIT with my team and in collaboration with Boggiano Pico. This is a part of Foundation Donorione, a rehabilitation center in Genoa where there are kids diagnosed with autism and also other neurodevelopmental disorders undergoing rehabilitation and training. So we designed an entire setup, entire training for kids to be able to interact with the robot, pass objects, do joint tasks with the robot, but in a safe way, so that's why you see there's a screen so that nobody hurts each other. And this is how the training looks. There's always a therapist together with a robot, and the kid plays with the robot. But in the games that they're playing, we embed training of social skills. In this case, they are training either joint attention or visual spatial perspective taking. This is a mechanism of cognitive mechanism, the ability to understand that your perspective is different than mine. Mine left is your right. And this is an ability that children with autism very often either develop much later than neurotypical kids, or they don't develop this ability. And this is underlying very many other social cognitive mechanisms or social interactions. So if we manage to train this kind of mechanism, maybe that will have a ripple effect for other social mechanisms and social interactions overall. So let me just show you very quickly how the training looks. The kid has a cube, passes to the robot, and needs to tell what does the robot see. They need to understand that the robot sees different side of the cube than the kid. So we have extremely promising results after a year of training of kids with autism, and we show that actually ICAP-assisted training improves general cognitive skills of kids more than standard therapy, and also specifically social cognitive skills. And here I would like to highlight that the way we're testing those skills is with another human. So after the training, we test whether kids actually are able to use those skills in social interaction with another human. So they transfer the training from human-robot to human-human. And this is extremely promising, I think, and we hope that we can help kids with their social skills with a robot. All right, I would just like to conclude here with these few concluding points. Humans do sometimes adopt intentional stance towards robots. This might vary across people, and what we have seen is that kind of bonding scenarios enhances attribution of mental states towards robots. Robots' signals and behavior can be perceived as social. Remember the mutual gaze experiment. And then finally, social robots can be very useful for healthcare applications. I would like to thank my team at IIT, thank the funding agency, European Research Council, and thank you very much for your attention.